You flip a switch and the light turns on instantly. Simple. But here's the strange part. Nothing actually rushes through the wire the way you think it does. The electrons barely move, yet the energy arrives almost immediately. So if electricity isn't flowing like water, what is really happening? Richard Feynman showed that the picture in your head is wrong, and the truth is far more interesting. Most people grow up believing that electricity flows through wires in the same way water flows through a pipe. This idea feels natural because it matches everyday experience. We open a tap and water comes out. We flip a switch and light appears. Because the result is immediate. The mind creates a simple picture of something traveling from one place to another. But this comforting image is misleading, and Richard Feynman often warned that such easy explanations can block real understanding. Electricity is not a substance being poured through a wire, and thinking of it this way hides what is actually happening at a deeper level. The wire is not a hollow tube, and electricity is not a fluid that rushes through it to deliver energy on demand. The reason this misconception is so common is that our language encourages it. We use words like current, a flow, and power, which sound like something moving continuously from a source to a destination. These words are useful for calculations and engineering, but they quietly shape a false mental model. In reality, the electrons inside a wire are already present long before any switch is turned on. They are packed closely together, interacting with atoms and with each other, and they do not suddenly sprint across the wire when electricity is used. Their motion, on average, is extremely slow, often measured in millimeters per second. If electricity truly worked like water in a pipe, everyday devices would respond with noticeable delays, which clearly does not happen. Feynman emphasized that confusing a helpful analogy with physical truth is a serious mistake in science education. The water analogy works only up to a point, and beyond that point it becomes harmful. It suggests that energy is carried by fast, moving particles traveling long distances, when in fact the behavior of electricity is governed by electric fields that exist throughout the entire circuit. When we hold on to the flowing water picture, we stop asking deeper questions, such as why a light turns on almost instantly, or where the energy is actually stored and transferred. The analogy becomes a substitute for understanding rather than a stepping stone toward it. By challenging this misconception, Feynman was not just correcting a technical error, he was teaching a broader lesson about learning itself. Real understanding requires the courage to abandon ideas that feel obvious but are wrong. Electricity shows us that nature does not care about our intuitive pictures. It follows its own rules, and those rules are often stranger, subtler, and far more interesting than the stories we tell ourselves to feel comfortable. One of the most surprising facts about electricity is that the electrons inside a wire move incredibly slowly, even though the effects of electricity appear almost instantly. This seems impossible at first because we naturally assume that something must be racing through the wire to deliver energy to a light bulb or a device. Richard Feynman loved pointing out this contradiction because it forces us to question our assumptions. The average speed of electrons, known as drift velocity, is often slower than a walking human, and sometimes slower than an insect. Yet the moment a switch is flipped, the bulb lights up without any noticeable delay. If electricity depended on electrons traveling from the power source all the way to the device, this immediate response would not be possible. The key to resolving this puzzle lies in understanding electric fields. When a circuit is completed by turning on a switch, an electric field is established throughout the entire length of the wire almost at once. This field already has electrons everywhere ready to respond. Each electron only needs to move a tiny distance to influence its neighbors, transferring energy through countless local interactions. It is not the electrons themselves that race across the circuit, but the change in the field that spreads rapidly, close to the speed of light. Feynman often compared this to pushing one end of a long rod. The atoms in the rod do not travel from one end to the other, yet the motion is transmitted quickly through the forces between them. This idea feels strange because we are used to thinking in terms of objects moving through space. Fields, by contrast, are invisible and intangible, so they are harder to picture. But they are central to how electricity works. The electric field tells each electron how to move, how much force it feels, and how it interacts with surrounding charges. Energy is passed along through these interactions, step by step, without requiring long-distance travel by individual particles. This is why electrical signals can travel extremely fast even though the particles themselves crawl along. Feynman believed that accepting this counterintuitive reality is an important part of learning physics. It teaches us that speed in nature does not always mean fast moving objects. Sometimes it means fast communication through a system that is already in place. Electricity demonstrates that energy transfer can be rapid even when matter moves slowly, and understanding this distinction helps replace vague intuition with a clearer, more accurate picture of how the physical world truly behaves. One of the most counterintuitive ideas about electricity is that the energy we use does not primarily travel inside the wire itself, but through the space surrounding it. This sounds strange because wires feel solid and important, while empty space seems irrelevant. Yet Richard Feynman emphasized that focusing only on the wire hides where the real action occurs. The copper in a wire mainly serves as a guide, shaping how electric and magnetic fields form and move through space. When a device is operating, these fields extend outward from the wire and carry energy from the source to the load. The wire's role is to keep the charges in place so the fields have a stable structure to follow. This concept challenges our everyday intuition because we are trained to think that energy must be contained within physical objects. However, in electromagnetism, energy is stored and transported by fields. The electric field represents how charges influence space around them, while the magnetic field arises from moving charges. Together, these fields form a pattern around the wire, and it is within this pattern that energy flows. Even though we cannot see or touch these fields directly, their effects are measurable and real. Feynman enjoyed pointing out that ignoring invisible things, simply because we cannot see them, is a poor strategy for understanding nature. This field-based view of electricity also explains why factors like insulation, wire spacing, and circuit geometry matter so much. If energy traveled only inside the metal, the space around the wire would be irrelevant. But in reality, changing the environment around a wire changes how the fields behave, which in turn affects how efficiently energy is transferred. At high frequencies, this becomes even more obvious as energy can radiate away from wires as electromagnetic waves. The surrounding space becomes part of the circuit, whether we acknowledge it or not. By recognizing that energy moves through space guided by fields, we gain a deeper appreciation of how electricity actually works. The wire is no longer the star of the show, but a supporting actor. This shift in perspective is uncomfortable at first because it replaces a solid, visible object with something abstract. Yet Feynman argued that true understanding often feels this way. Nature does not arrange itself to match human intuition. Electricity teaches us that empty space is not empty at all, and that the most important processes can happen in places we are not used to looking. One of the deepest lessons Richard Feynman tried to teach through examples like electricity is that true understanding begins where intuition fails. Human intuition is shaped by everyday experiences with solid objects, flowing liquids, and visible motion, so we naturally try to explain everything using these familiar ideas. While such analogies are useful at the beginning, they can quietly turn into obstacles when we mistake them for reality. Electricity feels simple because we use it constantly, and that familiarity creates the illusion that we understand it. Feynman warned that this illusion is dangerous because it replaces curiosity with comfort and stops us from asking the questions that lead to real insight. In science education, many explanations are designed to make students feel at ease rather than intellectually honest. We are given simplified stories that work just well enough to solve basic problems, and then we are encouraged to move on without questioning them. Over time, these stories harden into beliefs. Electricity flows, current moves, and power is delivered, all without ever examining what these words actually mean. Feynman believed that memorizing such language without examining its limits produces what he called a false sense of understanding. You can repeat the explanation, use the formulas, and still have no clear picture of what is truly happening. Letting go of intuitive but incorrect ideas is uncomfortable, and that discomfort is precisely why many people avoid it. Real understanding often replaces a neat mental image with something abstract, incomplete, or strange. Fields, probabilities, and interactions do not feel as satisfying as simple mechanical pictures. Yet Feynman argued that science is not about making the world feel familiar. It is about describing it accurately. Accepting that nature behaves in ways that defy common sense is not a weakness, but a sign of intellectual honesty. Electricity is a powerful example of this lesson because it works perfectly even when our explanations are flawed. The light still turns on, the phone still charges, and the equations still give correct answers. But if we stop at that level, we miss the deeper beauty of how the world actually operates. Feynman encouraged learners to constantly ask where their explanations break down, because that is where learning truly happens. Understanding electricity and science more broadly means learning to live with uncertainty, to question familiar ideas, and to accept that the universe does not owe us simple pictures.